Okay, welcome to a very special class. I believe you have a very nice day over there. In this class, we will be looking at the application of differential equation, exponential decay, and numeric growth precisely. And I would like to use my um, illustration from Newton's law of pulling. And at the end of the class, should be able to solve problems under this topic. I would like to talk a little bit about differential equation. Now, now let's look at the assumption of the bacterial population. First, let's start to talk about exponential growth before we talk about the exponential decay. All right, so if we are talking about exponential growth, we consider the population of let's say the population of a bacteria P. If we are talking about the population of a bacteria to be P, let's say in the first instance, P has a total population of 1,000. And also, let's also have this understanding, a belief that this bacterial system will duplicate after an hour to have about 600 increment of the size of the initial population. So that means the rate of change P prime after 1 hour equals to 600. So that means the total population, let's call it PT, after 1 hour is 1,600 bacteria. Okay, that means if we double the population, and we have P plus P, and that means we have a total size of the population to be 2,000. That means the rate of change of the new population, let's call this new population PT. Okay, that means the rate of change, the increment that this new population will, the growth rates, yeah, let's call it the growth rate of this new population now will be P prime, should be something like P prime P prime of the total T, and that will be equals to that. Remember the first one was 600, that means double of 600 will be 1,200. Okay. So that means the total uh, uh, new population, let's call that P T small n, meaning new population, will be equal to 3,200. Now, this is happening after maybe an hour when we double the population. Let me start again. Let me start the illustration again. Let's say we have a population P of a bacteria, a certain bacteria, and let's say the population at this point, P naught, at the time T equals 0, the population is equals to 1,000 bacteria. And let's say that the growth rate is that after an hour, the population will have about an increment of 600 other bacteria. So that means after 1 hour, the total population that we have would be about 1,600 in total. So I said, if I double this population and we take another 1,000 population of this bacteria and double them together, we have 2,000. So if we do that, then we also have that the population, the total population increment, I said that let's call this T prime. All right. So we have the rate of change or growth rate of the population. The new population will be 600 plus 600 for each of the population size. So we have about 1,200 growth rate of the bacteria. So that means the total at the end of the time frame The total population of bacteria we will have after doubling this population will be about 3,200. Okay, so using this idea, we can say that in a mathematical sense, the rate of change of the population with respect to time, t, is proportional to that means the more the population size, the more the increment. That is what I'm trying to show you. The growth rate increases according to the size of the population. So we can say when the growth rate, the population was 1,000, the growth rate was 600. So now we increase the population size to 2,000. The growth rate is now 1,200. It's also increasing exponentially. So we can say that the rate of change of the population, which is this, is directly proportional to the population size. Let's call that T. So yeah, if I take out the population, if I take out this, proportionality constant, I will have that dp over dt is equals to k and t, total population size. So, and that is making a whole lot of sense. And what can we say? This is a differential equation form. This is a differential equation that is formed already. Why? Because we have a, t, which is a function, and we have a rate of change also in the same equation, dp dt, now, which is the differential coefficient of a particular parameter, p. So how do we have to solve this problem? Okay. We as well, we can make it look like we are dealing with population. Let's say we can say this thing is take off this and take off this. Let's make it plain. So this equals to P and this equals to KP population. So that makes sense. That means the rate of change of this is directly proportional to the population size. Okay, so how do we solve this particular differential equation? So the method of solving this particular differential equation is what we'll be doing right now. But before we do that, before we do this, we will have to look at certain things and put them into construction. So let's solve that differential equation. So if we have dp over dt to be equals to k and p, I'm going to use separation technique of differential equation. So I'm going to move this and multiply. I'm going to multiply 1 all over p to both sides of the equation. Both sides of the equation. All right. This is what I mean. I will say 1 over p times dp over dt, then equals 1 over p times kp. All right, so that we can see that p here can cancel this. And at the end of the time, we have dp over p dt equals to only k. All right. At this time too, I'm going to multiply both sides by dt. So I'm going to multiply again, multiply both sides by dt. Okay, if I do that, I will have dt times dp over p dt equals to k times dt. So the t will take care of the t, and we now have that the p all over p now equals to k dt. Remember, the k is a constant. All right, now I'm going to introduce integral to both sides of this equation. I'll introduce integral, introduce integral to both sides of this equation. All right, if I do that, I will have integral dp all over p equals to integral k dt. You know what that means? Of course, to integrate, I'm going to move this constant out of this. And this one is the same thing as integral 1 over p dp equals to k integral and dt. All right. So that will now be equals to this one, the rate of change that we did with this on our primary integration technique. So if we deal with this will give you 1 upon, this is ln of p, ln p equals to, this is kt. Since there is no limit to this integral, that will put plus c here. Plus c. This plus c is a arbitrary constant if you are familiar with your integration. So and that also, so what we have there is, I'll repeat that here, ln of p equals to kt plus c. Remember that this is the same thing as logarithm over base e of p equals to the exponential, no, not that yet. So equals to kt plus c. So transforming this to its initial form. So take exponent to both sides of the equation. Take exponent to both sides of the equation. The both sides of the equation we have ln of p, or exponential of ln of p equals exponential of kt plus c. So exponential ln p is p. That means the population equals to exponential kt plus, this is t, plus c, which is the same thing as p equals to exponential kt plus, okay, let's remove this plus this time and replace it with multiplication. Let's obey the law of indices that is placed there. So we have times exponential of c. All right, so we can call this constant, ordinary constant. So I would say let exponential of c equals to p naught. What that means is I want to define the p naught as the initial position or initial value result or initial value of the population at time t equals to 0. So according to this problem, so I would say this is the same thing as p equals to exponential kt times p naught. So which finally we consider for the population p, which is a function of time, is equals to p naught exponential k and t. All right. So this is how to really solve that kind of a problem concerning exponential growth precisely. In our next video, you will see how to use this formula to really solve problems that have to do with Newton's law of cooling, which is, the problem is here already. Don't fail to look at the Newton's law of cooling, because we will really use that formula derived to solve this set of problems. I'm going to show you step by step. All right. First, don't forget to click on the subscription button so that by the time we start solving this particular problem, you won't be missed out. And you also have to understand at the end of this kind of lesson how to apply differential equation to practical problems or real life. Thank you and have a nice time.